Hello everyone, I'm going to present DGCL, an efficient communication library for distributed GNN training. Nowadays, graph neural networks are widely used in many areas, including social network, physics systems, and medical molecules. GNN learns the property of vertices and edges in a graph and have wide applications. For example, it can be used to predict the relationship between two users in a social network or to determine the similarity between two molecules. GNN is a kind of neural network. Now let me introduce how to train a GNN. Here we focus on the full graph training, which involve all the vertices in an iteration. Like other neural networks, GNN has multiple layers. At the beginning, each vertex in the graph has a feature, which is a vector to describe its property. Let us take a look at the computation procedure of a specific vertex, the blue one. In each layer, it aggregates the feature of its neighbors and update itself to produce a new feature for the next layer. It follows an aggregate and update computation pattern in each layer. Different GNNs have different aggregate and update function. Like other neural network, training GNNs is very computational intensive. It's better to train them on GPUs. The focus of this work is to train GNNs on multiple GPUs. In the distributed setting, we first partition a graph to several GPUs, and each GPU chain is corresponding subgraphs. However, during the partitioning, we cannot avoid that the endpoints of some edges are partitioned to different GPUs. Therefore, to guarantee the computation correctness, each vertex needs to fetch its neighbors on other GPU before the aggregation. Specifically, GPUs need to perform an irregular communication to fetch the features of some vertices from others. So in the distributed setting, the commutation pattern of one GPU layer is changed to communication, aggregation, and update. There are systems designed for full graph GNN training. DGCL and PYG are designed for GNN training on a single GPU. They are on top of TensorFlow and PyTorch and provide efficient kernels to process the graph data. NeoGraph and RC focus on distributed training. However, this system integrate communication and computation in the system. Therefore, the communication layer is not general to use. What's more, this system use naive communication strategies, which are inefficient due to the complex GPU topology. Therefore, we want to build a general and efficient communication library for GNN training, so that if a system can train a GNN on a single GPU, it can use our library to extend to multiple GPUs. And the library also have efficient optimization compared with naive communication. Now, let's see why the naive communication strategy is not efficient on GPUs. Peer-to-peer communication is the most straightforward strategy. In peer-to-peer communication, each GPU fetch the required vertex from other GPUs directly. However, it has two problems because of the complex GPU topology, which are the unbalanced communication and bandwidth contention. Let's use the DGS GPU server as an example. There are 8 GPUs on 2 CPU sockets in the server. Some GPUs are connecting with NVLink links, while others may need to go through PCIe and QPI links. Different connections between CPUs have different bandwidth. Therefore, in a peer-to-peer communication, fast links may need to wait for the slow links, which lead to unbalanced communication. What's more, different GPU connection may contend for the same link during the communication. For example, if we want to send some data from GPU 1, 3, 4 to GPU 5, they all need to go through the same PCIe to the same QPI link. which means they will contend for the QPI bandwidth. Therefore, we provide the communication time while using peer-to-peer communication to train a two-layer GCN on two datasets. The dashed line are the average communication volume on each GPU, and the black bar is the computation time. The shadow bar are the communication time. As we can see in the figure, although the average communication volume on each GPU are decreased when using more GPUs, the communication time keep increasing and dominate the training time when using 16 GPUs. To further explain the effect of unbalanced communication and bandwidth contention, we make a breakdown analysis on peer-to-peer communication. First, we provide the speed of GPU communication on different links. As we can see in the table, different GPU connections have different speeds. We also provide the communication time on every link and other links in a peer-to-peer communication. As in the table, the communication time spent on different links are unbalanced. The communication on the slow link are the stragglers. To study the effects of bandwidth contention, we can provide the attainable bandwidth when different number of GPU pairs using the same QPI link. As in the table, when more GPU pairs are using the same link, the bandwidth drops almost linearly. Therefore, the bandwidth contention is a severe problem in peer-to-peer communication. Motivated by the communication problems of peer-to-peer communication, we designed DGCL, a general and efficient communication library for GNN training. Now, let me first introduce the system architecture of DGCL. In the figure, the dark green parts are the components of DGCL, and the light green parts are the components outside DGCL. At the beginning, DGCL read the input graph and GNN models from users, and then it partitioned the graph and planned the communication. The DGCL master sent the subgraphs and communication plans to each DGCL client so that they can communicate with each other according to the plan. Finally, the GNN systems can do the training as in a single GPU and use DGCL for communication. Therefore, DGCL is general for different GNN systems. Now, let me introduce the design of the communication planning. First, we formulate the communication and then define the communication strategy of each vertex, which is the solution space. Next, we build a cost model to estimate the cost of communication strategy and use the cost model to guide the algorithm. In the problem formulation, the inputs of the problem are the graph partitioning scheme and the GPU topology. And we want to design an algorithm to do the communication planning for each vertex while considering the communication balancing, contention, and the forwarding. Finally, our objective is to minimize the end-to-end communication time. Given the problem setting, now let's analyze the solution space, which is the communication strategy of each vertex. Let's use a simplified GPU topology as an example. Assume we have 4 GPU on 2 CPU sockets connecting with different links. Assume a vertex is partitioned to GPU 1 and GPU 2, 3, 4 have its neighbor, which means we need to send this vertex from GPU 1 to 2, 3, and 4. So what are the possible communication strategies? A most straightforward way is to send from GPU1 to others directly as in the peer-to-peer communication. However, it may need to go through the QPI link to reach GPU 3 and 4. Another strategy is always to use the NV link and use GPU 2 and 3 to forward the vertex to GPU 4. A more complicated strategy may lie we send the vertex from 1 to GPU 2 and 3 and let GPU 3 to forward into GPU 4. As we can see, all the strategies of the strategic space of a vertex is a tree, and it's easy to prove that the optimal strategy of a vertex is always a tree. So, given the solution space, we use a cost model to guide our algorithm. So what is the cost model? Assume we know the strategy of all the vertices. In our cost model, we first partition the communication strategies into stages, and we assume the communication on the same stage are happen at the same time. So in each stage, we know the number of vertices going through each link and the speed on each link. So we can easily calculate the communication time on this stage, which is the maximum of vertices count over link speed of all links. By aggregating the cost of the stages, we can get the overall cost for the communication. Therefore, in each stage of the cost model, we only consider the slowest link, which encourages our algorithm to balance the communication on different links to minimize the stage cost. Also, all the communication on the same link are aggregated together at the same stage so that the connection is considered naturally in our cost model. Given the cost model, we design a shortest path spanning tree algorithm to determine the strategy for each vertex. The idea is that we incrementally process the vertices one by one. So the heuristic here is that we try to minimize the aggregated cost when deciding the strategy of a vertex. So when we process a vertex, we know the strategy of previous vertices, which means we know the cost of different links at each stage in the cost model. So now let's assume that the vertex is partitioned to GPU. The current vertex is partitioned to GPU1 and is requested by GPU2, 3, and 4. From the cost model, we know that if we associate a vertex on the link at a stage, the total cost may increase. So we associate each link a weight of cost increase if we assign the vertex on it. At the beginning, we find shortest path from GPU1 to GPUs 2, 3, and 4 with respect to the cost increase of the cost model. Let's say GPU2 have the smallest cost increase among those GPUs. Then we send the vertex from GPU1 to GPU2. And now GPU1 and 2 all have the required vertex. We use them to find the shortest cost path to GPU3 and 4 and pick the communication path with smallest cost increase. Let's say it's from GPU2 to 3. Similarly, we run the shortest path again, and finally we get a spanning tree, which is the communication strategy of the vertex. The intuition behind the algorithm is that each time we extend our spanning trees to GPU with minimal cost increase. So we conducted experiment on two types of machine, two servers with a V100 GPU connecting with NV links, and a server with a 1080 GPU connecting without NV links. We compare with three communication baseline, peer-to-peer replication and swap. Replication baseline replicate k-hop vertices for one GPU to eliminate the communication. Swap baseline use host memory as the shared memory for communication. We use the dataset of large graphs, including Reddit, Web Google, Wikitalk, and COM-OCUD. The GNN model includes GCN, CommonNet, and GNN. We first compare the end-to-end performance to train GNN on different data sets on AV100 GPUs. In each group of the figure, we provide the performance of DGCL, swap, peer-to-peer, and replication baselines. In each part, the bottom part is the computation time, and the upper part is the communication overhead. From the figure, we can see that DGCL has significantly shorter communication time than peer-to-peer and swap baseline. average across all graphs and models, the communication time of peer-to-peer is up to 4.5 of DGCL, while the swap is up to 60 times of DGCL. The peer-to-peer, the per apple time of peer-to-peer and swap are 1.5 times and 7.4 times of DGCL. The replication baseline only have comparable performance on sparse graph like WebGoogle. We also reported performance of DGCL on GPU topology without any link. In such case, the GPU connections have similar bandwidth, but DGCL still outperform peer-to-peer communication since it considers the bandwidth contention during the communication. We also used a micro experiment to test the coarse model accuracy. We run our planning algorithm on different graph size on Reddit and WebGoogle. The graph size is changed by randomly remove some vertices. We report the relation between the coarse model and the real communication cost. The results show that the actual communication time has a linear relation with the estimated communication cost. We also give a breakdown of the communication time that DGCL spend on different links. The results show that DGCL can effectively balance the communication time spent on different links. Now, let me give a brief conclusion. We start from a communication problem in GNN training and give an analysis of peer-to-peer communication. Then we propose a general communication library with coarse model and planning algorithm. Finally, experimental results show that DGCL outperform other baselines on different data sets. GNN models are and GPU topologies.